This will be the follow-up to the previous video on advanced atomic structure. And the first thing I want to talk about is notation. So let's take, for example, in iron. Using Aufbau's principle, try and write the notation. Alright, here it is. So 1s, 2, 2s, 2, and I'm going to explain what all of this means very soon. 2p6, 3s2, 3p6, 4s2, 3d6. Okay, so you can basically break this down into n and then one of the shells, which can be s, p, d, or f, and then this exponent, let's just put this as e here. So this first number, this n, tells you which shell you're in, right? So in the first shell, we only have an s orbital, and e tells us the total amount of electrons all of this type of orbital is holding. So this means in the second shell, the s orbital holds a total of 2 electrons, and same here for 3p6. So in the third shell, the p orbital, since there's 3 of the p orbitals, they're holding a total of 6 electrons. And you can notice here something weird is the 4 comes before the 3. And this links to my previous video where I talked about Aufbau's principle, where it's easier to open up a new shell and go to that new shell than to fill up the previous shell. Alright, so if you're not quite sure and you don't quite understand, I'll leave a link to my previous video. Alright, so what does this actually tell you? What can we do with this? Well, there's something called ionization order. It's basically telling you if electrons come off, where does it come off first? So let's think about this logically, right? If the shells represent how far the thing is from the nucleus, so I'm not going to draw all the electrons, but I will draw all of the shells. So we have 4 shells here, and we have 2 electrons here. I'm only going to draw the outer ones. Where do you think that, let's say, another atom comes in here and they want to ionically bond, so they want to take away iron's electrons? Where are they going to take it from? This notation might make you think it's this one, but we should still think about it a little bit more. They will always just take it from the outermost electron, because if you take it from the outermost electron, the nucleus is having the weakest force on this. It's pulling the electron the weakest, and it's closest to the outer electron, the other atom that's trying to pull off the electron. So that's what's happening during ionic bonding. And one more thing I want to cover here is that certain shells at certain points are very strong. So you typically see iron 3 and iron 3 plus iron 2, but we rarely see anything like iron 4 or iron 5. In fact, they're practically non-existent in the natural world. The reason this is, let's look at this. Even if we take off, so we take off 3 electrons, for example, because it's 3 plus, so those 2 electrons are gone, and we take off 1 from here, and we're left with this structure. And you'd be right to doubt, now hang on a minute, why doesn't the electrons go from the D shell back up to the 4th shell? Because I originally said that that's the easiest thing they want to do. Now normally, yes, you'd be right, but in this special case, for example, in the D shell, the D shell can hold a total of 10 electrons because there are 5 D shells, and each shell, 5 D orbitals, and each orbital holds 2 electrons, so it's total of 10 electrons, so it can hold a total of 10 electrons. Notice that right now it's holding 5 electrons. So whenever D is holding 5 electrons, it's also incredibly stable. So it doesn't want to lose anymore, it doesn't want to gain anymore, and that's why iron is so comfortable being in 3+ or 2+, because in that configuration, the shell basically just has 1 electron for every orientation it can be, and every orientation it can have 2. So basically, a half-filled D shell is extremely stable, and it explains why iron 3 exists, but iron 4 doesn't, iron 5 doesn't exist. Well, not that they don't exist, it's just they're increasingly rare. So that's about it. That's everything I wanted to cover, and now you know advanced atomic structure.